Hello student, in this video I am going to talk about, or we are going to discuss about a example that is about addressing the CERN problem with tree induction. So what is the problem actually? That is the CERN problem. So you can go through few videos earlier where we have mentioned about this problem, but also I can remind you of that problem. Here you can see it is basically about predicting whether a person will leave a company within 90 days of contract expiration or not. That is the problem, to predict whether a person will leave a company within 90 days of contract expiration. So mainly it is about churning. Churn mean burnout. Those people who will go out, that means those are churn people, and who will stay, they will stay in the company. So now prediction is about who will go out and who will stay. So in that situation, we'll try to build a tree. So here for this example, suppose we have historical dataset of 20,000 customers. At the point of collecting the data, each customer either had stayed with the company or had left. So that is about the data. The data consists of 20,000 customers values, and each customer either had stayed or left. Means two class. Each customer is described by variable listed in table 3.2. So according to this variable, dataset contains these variable. So explanation of those variable like this: college is the customer educated from college, income, what is the income of the person, what is the overcharge, average overcharge per month, leftover minutes per month, house, estimate value of dwelling for census tract. So these are the variable which have been kept in the data set. Now what they try to do initially, they try to estimate the probability estimation. So they applied a Laplace smoothing on probability estimation for several instance ratios. Okay, so here you can see the probability estimation for number of instances, samples, and they try to apply the effect of, or try to find the effect of Laplace smoothing on probability estimation on for several instant ratios. Actually that estimation you can find out through these text, how it goes through this estimation, as we have discussed about various probabilistic model. You can understand if you go through this text, and also how they have applied Laplace smoothing. That is your homework, but we are more focused on how we can create a tree induction depending upon the data we have. So our variables, or you can say attributes, are like this. So these variables comprise of basic demographic use information available from the customer application and account. So we are going to use this data in our tree prediction technique. So the results in figure 37, 317, if you go through that, 317, okay, here you can see what it describes with a table listing exact values. As you can see, that first three variables, the house value, number of leftover minutes, number of long calls per month, have a higher information gain. We have discussed about information gain in earlier videos, and try to go through that also if you don't understand about information gain. But it has a very important role while we choosing the ranked attribute, high ranked attribute for our classification purpose. So here it says that according to the figure 317, these three values or three attributes have high information gains. Perhaps surprisingly, neither the amount of the phone is used nor the reported degree of satisfaction seems in and of itself to be very predictive of charming. So applying a classification tree algorithm data, we get the tree shown in 318. So we'll go to the figure 318. So that is this one. They try to create this tree. Now how we can create this tree, we'll try to understand that. So the highest information gain is feature, information gain feature is house according to 317 obviously, and is at the root of the tree. So it will be at the root of the tree. House has the highest information gain. Then the next information gain will be in that phase. So house has highest information gain, but they are not considering about long calls per month or leftover, because that does not play any role in the classification process, as it has mentioned in this line. Perhaps surprisingly, neither the amount of phone is used or nor a reported degree of satisfaction seems in and of itself to be very predictive of churning. So those are not considered in this case. So that is why after house they will go for overage, also high in the tree. However, the order in which features are chosen for does not exactly correspond to their ranking. So next choosing features, the order in the order of the features chosen for the tree does not exactly correspond to the ranking in the figure 317. Why is this? Why is this? The answer is that the table ranks each feature by how good it's independently. That is very important point. How good the feature is independently, evaluated separately on entire population of instances. Means those ranking if you have seen in the graph here, has been applied on a separate population, or you can say instances, sample of instances. Nodes in a classification tree depend on instances above them in the tree. So any node in a classification tree depend on the instances above them in the tree. Therefore, except for the root node, features in the classification tree are not evaluated on entire set of instances. The information gain of a feature depends on set of instances against which is evaluated. So the ranking of features for some internal node may not be same as global ranking. That is the main point. Okay, while we choose the next nodes, those nodes or the ranking of those attributes might not be global. In the global scenario, the ranking might be high or lower, but in case of finding the next node or the specific ranking of a feature is find out by applying on a subset of features. So here you can see the information gain of feature depends on this set of instances against which is evaluated. So that might not be the whole instances. So the ranking of features for some internal node may not be same as the global ranking. That is why you can see in the tree here that overage, though in this case overage come here, but and again this income is here, it comes after house, and a house, the tree is divided in that direction if it is less than or equal 600,469 or greater than 600,469. And then overage, in that also after that they try to put this leftover feature. So but leftover feature might have higher ranking in global scenario, but in partial scenario overage has highest ranking for some instances, so for some set of instances. So in that way they try to build a tree. So we have not discussed how we decide to stop by building the tree. That is, the dataset has 20,000 example, yet the tree clearly does not have 20,000 leaf nodes. Can't we just keep selecting more attributes to split upon, building the tree downwards until we have exhausted them? The answer is yes, we can, but we should stop long before the model becomes that complex. That is important point in case of tree creation for classification. This issue ties in closely with model generality and overfitting, whose discussion we differ in chapter 5. We will discuss about overfitting in a separate class. So here actually how it is created, if we go to the definitions of tree creation, here you will find tree as a set of rules. Here you can see, before moving on from its interpretation of classification trees, we should mention the interpretation as logical statement. Consider gain the tree shown at the top of the figure 315. So here figure 315 is what? Figure 315 is here. So gain. So if you go through that example also, you will find the same situation. You classify a new unseen instances by starting at the root node and following the attribute test downward until you reach a leaf node, which specify the instances predicted class. If we trace down a single path from root node to a leaf, collecting the condition as we go, we generate a rule. The rule will be like this: if balance is less than this and this is this, then class is write off. If this is this, then this. So like that we will go. Like here also you can find this problem also. If balance is greater than less than 50, then we will go to the this is if because after satisfying this attribute we will go for this attribute, and after applying this attribute we will try to write the class of that problem. Like here also, in this case also you can find here. Okay, so in that true, after house it try to find out average features, but here also they try to find income features. So this is a tree model they try to create, but if you go through this, you can create a different tree model to find out more accuracy. That is why because depending upon a tree, the accuracy will change. So that is a two question arises. Okay, one question is that here, do you trust this number? If we apply the tree to another sample of 20,000 people from this same data set, do you think we'll still get out 70% accuracy? Or if you do the trust the number, suppose you trust the number, does it mean this model is good? In other words, is a model with 73% accuracy worth using? So that is the point. How could you find a better model? So that is what about tree induction while we applying on classification problem. So try to go through this context. Okay, in the book I just give you a hint and brief about the idea how we can create a tree induction depending upon the gain of information, and you can go through very minutely through this book and how we can create the rules and how we can divide the classes, okay, and how probability estimation works in this scenario. Please go through that, and how this tree might change. Obviously this model, if give it only 73% accuracy, there might be scope to get 90% accuracy also. Then how can we get that? That is also a very big question. So try to go through this example. Okay, this is related about whole things we have covered in module 2. Thank you.